Okay.
Okay, so it is my pleasure to announce that Professor Fatih will continue with the session
Yeah.
of the first day of his Summability course.
Okay. Thank you. Thank you, Dr. Nakosa. Thank you. So we were at the beginning of the proof of this proposition, which says that an absolutely convergent series converges. As I said before, we will be using this series of positive part of the terms and the negative parts of the terms of series. Okay. So let's start with the absolute convergence of the series. If an is absolutely convergent, then by the definition we write that this series is convergent, right? So it satisfies the Cauchy condition. And since we can easily write the coming inequality, which is which comes from the triangular inequality, holds the series AN also satisfies the Cauchy condition. And therefore it converges. So since AN is absolutely convergent, then it holds the Cauchy condition that we talked about before. So for each epsilon, this finite summation has to be less than epsilon. Yes. Yeah, I raised it. Okay. So this summation has to be less than epsilon, and we also have this inequality because of triangular inequality. So this implies that this summation has to be less than epsilon for all n and m's greater than cap n, that is defined in the definition of Cauchy condition. So this results in that the series itself holds the Cauchy condition, and because of it we say that it also converges in usual sense. For the second part, for the second part, we note that as we can remember that we wrote two equality here. The second one says that the whole series can be written as this addition of the infinite series of its positive part and its negative part. So sorry, it's my bad. What I tried to refer was this equality. We know that an absolute value of a real number can be written as the summation of its positive part and negative part. So we can write here this summation as the absolute value of AK. So it is also equivalent positive part of AK plus negative part of AKs. So because of this, we can also use because of the definitions, we can also have another inequalities in the following way. The summation of positive parts less than or equal to summation of the absolute value of AKs, and lastly summation of negative parts less than or equal to summation of absolute value of AK. So this means that the absolute value of AKs satisfies the Cauchy condition if and only if the parts in the middle holds the Cauchy condition. Okay, which shows that AN holds Cauchy condition if and only if the positive part of the summation of positive part of the series and summation of negative part of the terms hold both hold the Cauchy condition. So this implies that AK is the series of the absolute value of AK is convergent if and only if both positive parts and negative parts are convergent. So continuing in that way, in that case, we have the following inequality, equality, and runs from 1 to infinite by the definition equals the limit of the sequence of partial sums. Right? This is because of the definition. So it is equal to limit of the subtraction of these two sequence minus k runs from 1 to n, the negative part of AK. So as you can remember, we in somewhere, yes, it is. We use this equality. Any real number can be written as the subtraction of its positive part and negative part. So we take AK as the subtraction of its positive part and negative part, then we can distribute summation separately here. So from this we can also write the positive part of AK minus limit as n tends to infinite the negative part of AK, which is actually the infinite series of the positive part of the terms minus the series of negative parts of the terms. So with the same manner, we can say that the series itself is convergent if and only if the series of positive parts and the series of negative parts is convergent. Since this is a finite number and this is a finite number, then the subtraction of this number gives us the summation of this series itself. Okay. So So it will be, I will be giving you an interesting example related to natural numbers and using these positive parts of sequences and negative parts of sequences. So we have a remark here underlining the importance of completeness of the spaces that we are dealing with here, because without completeness of the space, the Cauchy condition does not work out. I'm going to explain it with an example. So we believe that it is it's worth noting that these results depend on the completeness of real numbers. The following example explain this perfectly for spaces that are not complete. I mean, the very first non-complete space that come in one minds is, as you know, rational numbers with usual metric, which is absolute value of numbers. Suppose that we have a sequence which have positive natural numbers as its positive part and its negative part. Suppose that an and an minus belong to positive natural numbers such that positive rational numbers such that the series of positive parts is summable to root square 2 and the series of negative parts equal to 2 minus square root of 2, and as that hold. Now we can write an, I mean the sequence whose terms as the subtraction of positive parts minus negative parts. So we have this equality. Then the whole series is equivalent to subtraction of the series of positive parts and negative parts, right? Okay. So this is, if we use this equality, as you can see, it is equivalent to, it is equal to times square root of 2 minus 2, which is an irrational number, right? Sorry. However, if we write the series of absolute values, then we have this equality. So if we sum the limit of this infinite series, we have 2, which is the sum of the absolute value of the sequences. See? As you can see, this number is in natural numbers, so they are not equal and they are completely different. One is in rational numbers and the other is in irrational numbers. So this series is convergent absolutely in rational numbers, but not convergent with usual sense in rational numbers. This is because of the incompleteness of rational numbers. So it is crucial, because of this, it is crucial to use the concept of completeness. Okay, there are other concepts of infinite series that I believe you came across before, but I will not be talking about them a lot. I don't want to bother you. I try to refer the parts that we mostly are gonna use in our courses. Now I would like to give you start the concepts of summability methods. I'm gonna start with sequence spaces. From now on, the spaces, the sets that we are be focusing on will be sequence spaces. Even though I talked about series here, series, infinite series, actually we mostly talk about the sets of sequences. Even though we say that infinite series, actually it is so clear that the concept of series comes from the concept of sequence. So we will be focusing on sequence spaces. So we know that there are many types of spaces in the mathematics. According to the measure that you deal with, you are gonna come across different types of spaces. For sequence spaces, we will be using a very fundamental type of spaces, which are vector spaces or linear spaces. After a certain point, we will be using the concept of normed spaces or metric spaces. But initially, we will be using just the concept of linear spaces for sequence spaces. So, firstly, I will I'm going to introduce you to the set of all sequences which don't have any condition on. Generally, we use this notation. Some prefer the letter S as well. Omega will be used for the set of all sequences. It comprises of the sequences xk such that x is a sequence whose range is R or complex numbers. Preferably, I will be using real numbers, but as I said before, many things that we will talk can be considered for complex numbers as well. So, this set denotes the set of all sequences of numbers. I'd like to point out that the main description for the whole sequences will be the concept of boundedness. Some professors prefer defining this set as the distinct union of all bounded and all non-bounded sequences. So we can consider it as the distinct union of bounded sequences and unbounded sequences. So sometimes when we say that the whole sequences, sometimes we say that the space of bounded or unbounded sequences. So it will be including all bounded and all unbounded sequences. This will be the main distinction here for us. Okay. Omega forms linear space or vector space over R with coordinate wise addition and scalar multiplication. Defined by and so thanks to this the operation of addition and the operation of multiplication with scalars, we say that this set forms a linear space. It can be easily confirmed that these two operations needs to be a vector space. So this is the crucial part of being a sequence space. So what is a sequence space? So since we make sure that the whole sequences, the set of all sequences, forms a vector space with these two operations, we can talk about subspaces of omega. We know that any linear space can have many type of subsets, but some of them who has some particular condition can be considered as subspace of it, right? So we will be focusing on the ones who are subspace of W. I mean omega, sorry. So definition. Each linear subspace of omega is said to be a sequence space. If A is a subspace of omega, we will denote this by this denotation. I mean, when we use the usual inclusion denotation, I mean this one, this implies that A is just a subset of omega, okay? But when I use this notation, then it means that A is definitely a subspace of omega, because we will be focusing on those ones. So any subspace of the set of all sequences is called to be a sequence space. So when we use the notation of sequence space, we have to remember that in the beginning, we don't need any type of distance function or normed function to call it as space. Being alone vector space is enough to call a set of sequences a sequence space. But after a certain point, we will have to use some type of norms or metrics to do further results or further definitions. Okay, examples, some examples and notations. The following subsets of omega are clearly sequence spaces. We start with the main distinction that I mentioned before, the space of all bounded sequences. Bounded sequences meets the particular definition of being a bounded sequence. So we can summarize it as follows. We will be using mostly this denotation for the set of all bounded sequences. Some put this infinity here, but I prefer personally putting it in here. And also some professors use this notation, so I just wanted to let you know, in some books you can run into this denotation as well for this space of all bounded sequences. So L infinity comprises of sequences such that the supremum of the absolute value of all terms is infinite. So this is also actually coming from being a bounded sequence. If a sequence is bounded, then we have finite supremum of all terms. Why we use this notation instead of writing just xk is bounded, it comes from the need that we will be using the concept of norm for sequence spaces. I'm going to call this particular norm as the supremum norm of all bounded sequences, all convergence sequences, and all null sequences, which are the sequences that converge to zero. So this is the space of all bounded sequences. So we will call this function as the usual norm of L infinity. Is called the supremum norm. It's called the supremum norm. Unless otherwise stated, we will be using this norm for the space of all bounded sequences all the time, because this is the usual trivial norm of L infinity. So the first subspace of L infinity is the space of all convergent sequences. So it contains all the sequences such that limit of xk exists. So this norm is also be used for the usual norm of the space of all convergence sequences. And very known subspace of the convergent sequences is the space of all null sequences. Xk equals to 0. Okay. So it is so clear that this space is included by the set of all convergence sequences. And I'm not going to write it again, but this supranom norm is used as the usual, as the trivial norm of both C and C naught. Okay, let me write here that this is the set of all convergence sequences, the space of all convergent sequences, the space of all null sequences. So I guess I believe it is worth noting that when we write just convergent, we mean the usual convergence of sequences, because in the more we advance, we will be using other type of convergence. When we refer to them, we will exactly write the type of that said convergence. But if we don't use any term other than convergence, then we mean just the usual convergence of sequences. Okay, now I guess I will be defining pretty new space that you might run into now. The space of all sequences with bounded partial sums. We generally denote it by BS, which comes from the first letters of bounded series. It comprises of xk's from omega, such that supranom of the sequence of partial sums is finite. So it is called the space of all sequences with bounded partial sums. And this function, this notation is denote the norm function for this space. Here, BS is BS norm of BS. Now, I believe you are going to be familiar with this space because we, before this part of my talk, we talked about infinite series, especially in particularly the convergent infinite series. CS comprises of sequences from omega such that xk is convergent. The space of all convergent or summable series. Maybe it would be better to write the space of all sequences with convergent partial sums. The space of all sequences with convergent partial sums. In some books or some authors or some professors sometimes prefer calling it the set of all convergent series, which is not wrong at all, but I personally believe it is better to call it the space of all sequences with convergent partial sums, because as I said before, we talk about sets of sequences, not exactly sets of series. So to me it might be a little bit more appropriate to call it the space of all sequences with convergent partial sums. So because of this, we could have written here the partial sum has a limit. So this is called the space of all sequences with convergent partial sums, or space of all summable sequences. And another important type of sequence spaces is called LP spaces. We will be using P's that greater than or equal to 1. LP is the space of sequences from omega such that such that this infinite series is convergent. This means that sorry, this should have been infinity, yeah. This means that this is convergent. The series of the power of p of the absolute value of xk, the absolute value of xk to the power p forms a convergent series. Then this is the space of LP, and here the usual norm of LP is defined as this. I mean, since this is convergent, this is equal to a finite number, so this is well defined, and it also needs to be a norm. So this is the LP norm. Yes, we will be using a particular one a lot, which we called before as the set of absolutely convergent series. It is equal to L1, which we take P as 1. It is the space of all sequences from omega such that xk is absolutely convergent. As you see, this is the definition of an absolutely convergence of a sequence, and we call it the space of all absolutely summable sequences. Yes, one can easily confirm that all LP spaces is included by L1 for each P. So I'm going to note it here. Proposition: let Q greater than P greater or equal to 1, then LQ is included by LP. An immediate result of this, or conclusion, for all P greater or equal than 1, we can write LP is included by L1. Okay, another type of sequence space is called the space of all sequences with bounded variation. It consists of sequences from omega such that okay, this space is called the space of all sequences with bounded variation. The map that we write here is called to be the V-worm of this sequence space is called the BV norm. An important subspace of this bounded, the set of all bounded all sequences with bounded variation is actually the intersection of BV and all convergent sequences. Sorry, all null sequences. Another important sequence space is the space of all finitely many non-zero sequences. It consists of sequences from omega such that after some certain index all term of the sequence is 0. So this space is called all finitely non-zero sequences. And most of the time we use this denotation for it, the phi. The space phi will be used for denotating of the space of all sequences with finitely many non-zero terms. The space of all finitely non-zero sequences. As I said, it means that some authors like calling it the tail of the sequence. The tail of the sequence is completely 0. This type of sequences is called to be finitely non-zero sequence. So there's an interesting result about the space phi. It is actually the span of the set of all unit vectors in omega. Here, e to the power n means this particular sequence of sequences with this definition. Delta n k is defined as if k equals n, then the term is 1, else it is 0. For example, the first term of unit vectors as we defined it delta n k, sorry, this doesn't look as delta. Okay. So the first term is equal to the first term of this sequence, so it is 1, others is gonna be 0. The second term of the second unit vector will be defined as this. The third unit vector will be defined as this. And the nth unit vector is defined as this. Here, 1 is located in nth term. En denotes the nth unit vector in omega, the space of all sequences. So we basically say that the space of all finitely non-zero sequences is in fact the span of the set of all unit vectors from omega. So now I believe I'm gonna write a particular chain amongst the most popular types of sequence spaces that I shared with you until now. One can, let me write it here, one can easily confirm that phi is included by LP for each P, that is included by L1, that is included by convergence series, that is included by C0, all null sequence space included by, let me continue from here, included by the space of all convergent sequences and it is equal to direct sum of C naught and the span of the sequence E, which is identity sequence, that is whose all terms equal to 1. I'm gonna write it down. And C is included by L infinity. I will be adding some new sequence spaces later, but not all of them can interfere between them. I don't know if I put it a good way. I love this chain, honestly, because this is a total chain. But for example, I cannot put the set of all sequences with bounded partial sums randomly. Okay, but as I said before, it is not that hard to confirm this chain. I mean, as I said, and another chain might be expressed as follows, and L is included by BV naught, sorry, BV naught, which is included by BV, which is the direct sum of BV naught and the span of E, sorry, and lastly C. Where the sequence E is defined by the sequence whose terms are all equal to 1. Maybe it might be worth noting that what was the name of direct sum of two subspaces of vector space. I'm gonna just remind it for you. Where and Okay. So this means that actually, for example, here, the space of all convergent sequences is actually direct sum of all null sequences and the span of the sequence with terms of ones. I mean, I was trying to point out that I cannot randomly put some sequence spaces between these inclusions. The second one actually is a good example of what I tried to say. Here, as you can see, by the way, this is exactly the same, the space of all absolutely convergent sequences. So the space of V naught includes all absolutely convergent sequences, and it is included by the space of all convergent sequences. But there are some examples that so there are some sequences that is in BV not, but that is not in convergent series. So that's why we cannot randomly put some spaces that we are familiar with in this chain. So the more we get advanced, we might need to write some new chains that are different from these ones. Another fundamental example of sequence spaces is the space of all sequences of zeros and ones. It consists of xk's such that xk belongs to 1 and 0 for all k from natural numbers. The space of all sequences of zeros and ones. So we just deal with the sequences with whose terms are just zeros and ones, not the sequences that having any other terms other than 0 and ones. This is the space of all sequences of zeros and ones. And thanks to this space, we define another sequence space, which is basically the span of this space. I will be using the M naught denotation for it. It consists of all sequences from omega such that the terms of sequence forms a finite set. As you can see, it consists of sequences whose range is finite. Now, I will introduce you to a particular concept regarding sequences. Thin sequence. Thin sequence. What is thin sequence? A sequence xk is called thin if there exists an index sequence kv with kv minus 1, sorry, yes, tends to infinity. As v tends to infinity, such that xk equals 1 when k equals kv and xk is 0 otherwise. I mean, if a sequence has a subsequence that has ones and zeros on the index such that the index holds this condition, it is called a thin sequence. I mean, not every sequence is thin, obviously. We are interested in the ones whose index, some sequences has ones and zeros on the index such that those index holds this condition. Then we call them a thin sequence. Further, the space of all thin sequences will be interest of ours. X is thin. So another type of chain might be written here. phi is included by the set of all thin sequences, and it is included by the set of all sequences with ones and zeros, and it is included by the span of all sequences with ones and zeros. Yes. I guess we can stop here if it is fine with you, because I will be starting a new title. So I just want to continue it tomorrow if it's fine with you, because now tomorrow we will be focusing on why we need to have summability methods, a different type of summability methods. So I would like starting this part tomorrow if it's fine with you. Thank you. Thank you for listening to me. I mean, it might be pretty challenging to listen to some people that long,